So we want to show that the average velocity for constant acceleration is the sum of velocities divided by 2. So let's say we have a constant acceleration. Let's make it 1. Let's let him play for a little while here. Let's consider between 0 and 2 seconds. So he starts off at 0. His velocity is going to start at 0 at time 0. The velocity actually was 0 in the beginning. They've already added a little bit of velocity here, just like they added a little position at 0 seconds. He's actually really at 0. His position is not 0.001. Somehow the simulation is a little more granular, so we can't really get to the actual 0 for whatever reason. But anyhow, that was the case. So how far has he gone at 2 seconds? Let's take him up to a time of 2 seconds, and his position is now 2. So in 2 seconds, from when we started the clock, he's gone from 0 to 2. So remember, the average velocity is the velocity that will take you through the displacement of interest, that is, the displacements that happens in the time interval under consideration. Here, the first 2 seconds. The average velocity is velocity that is the constant velocity that would take you from 0 to 2 in the same amount of, it would give you the displacement in the same amount of time. Here the displacement is 2. So what's the velocity that takes you in 2 seconds, 2 meters? It's 1 meters per second. So the average velocity that gets you from 0 to 2 in 2 seconds is 1 meter per second, right? Because at 1 meter per second, after the first second, you go 1 meters. Then at the next second, you go another 1 meters. Every second, you go 1 meter per second. That's what 1 meter per second means. So if you go 1 meter per second for 2 seconds, you go 2 meters. So the average velocity is 1 meter per second. And here, what would the initial velocity be? 0. Well, what's the final velocity at that time? 2. So the average is going to be the sum, 0 plus 2 is 2, divided by 2. That's 2 divided by 2 is 1. That'll give us 1 meter per second. Okay, so it worked in that case. Okay, that's great. Let's try a different case. I'll reset this thing. Maybe let's do something more complicated. Maybe I don't have to start him off with a 0 velocity. Let's say he starts off with a velocity of 2 and then accelerates at 4 meters per second. Let's see if we can get him to go for 2 seconds now. Well, hit the wall. Okay, he hits the wall in 2 seconds. But let's just consider the first second then. So I'll go from 0 to 1 second. So again, the initial position is 0 and the initial velocity is 2. This thing is granular, so it's not letting us quite get to that. But let's see what about 1 second later. So if we go to 1 second, so here we are at 1 second later, his position is 4. He's gone from 0 to 4 in 1 second. His velocity is 6 when it ends up. So his final velocity is 6. All right, so what would his average velocity be? So the average velocity is the constant velocity that gets you the displacement in the time of interest. Here it's 1 second. So the displacement is 4. The time of interest is 1 second. So you want 4 meters in 1 second. So the average velocity is clearly 4 meters per second. Okay, now let's see, does that make sense? His initial velocity is 2. His final velocity is 6. So we do 2 plus 6 is 8 divided by 2 is 4. That gives us the same average velocity that we can just see directly from looking at his journey right here. His average velocity had to be 4 meters per second. That's the constant velocity that does the same displacement that the variable velocity did over the interval. So we've just pretty much demonstrated here for those couple of examples, and we could keep doing more. So the last example we just looked at, we had the average velocity was 4. Remember, the initial velocity was 2, plus the final velocity we saw was 6 1 second later, and then divided by 2. And this gives us 4, and the units are meters per second. This is 2 plus 6 meters per second divided by 2 is 4 meters per second. So we could do some more examples like that where we're just testing it off, where we can physically see from the simulation that this is the case when acceleration is constant. And this will allow us to get a couple more equations. So what more equations could we get here? One thing we could do to get more equations, always want more equations apparently, is I could just go ahead and replace the average velocity with the initial and final velocity over 2 right here. So this x equation, so going from 1, so going from here, I'll have wherever you start off at, x0 plus the average velocity. But now my average velocity, I'll write it this way, is v plus v0 over 2 times t. Or I could write it like this. Let's see, it's going to be x0 plus v0 over 2t plus v over 2t. Alright, but here I have the final velocity. What I actually want to get here is final values, that is, in this case I want to know the final position in terms of initial conditions. So let's say I'm given initial conditions, x0, v0, and possibly even a. Here, we're not given the final velocity, we're just given the initial velocity. And we have this pesky final velocity sitting here, but how can I get it? Oh, I have it right here, so I can just replace him right there. So I got one more thing to do. Then I'll just substitute in that for my v, and I'll write that 2 out the side here, t over 2. So what'll that give me? Well, if I distribute the t over 2 here, I can see I'm going to distribute the t over 2 between the two terms in this parentheses. I'm going to have v0 times t over 2, but I've already got a v0 times t over 2 over here. So that's going to be 2 of those, so I'm going to have a half plus a half is 1, so that's going to give me one of those. So I'm going to have, okay, the x0 I still got, plus I'm going to have this term plus the term coming from distributing the t over 2 between those terms is going to give me just a v0 t. And then what's left over in here, I'm going to have a times t over 2. That's going to be 1/2 at squared. So that is going to give us another kinematic equation, and you know what, maybe we're going to call him kinematic equation 4. Okay, here's 1, 2, 3. Well, I could call him kinematic equation 4. So anyway, I have one more kinematic equation to cook up, and then we'll be done deriving the kinematic equations that we get in our textbook. Here we have 4 of them. There's one more kinematic equation that they derived for us in our textbook. We'll go ahead and get that one. So before we derive our final equation for 1D kinematics that we're going to derive from these 3 basic starting equations, by the way. So this equation 1, 2, 3, that is the complete 1D description of kinematics for constant acceleration. And this other equation, here this equation 4, and the final equation, which we'll call 5 when we finally get to it, that we're going to derive from the first 1, 2, 3. Because remember, how did we get this equation here, x equals x0 plus v0t plus 1/2 at squared? We got that by first eliminating the average velocity in the first equation from the third equation. So I just substituted this average velocity in here. And then I eliminated the final velocity from this equation here in terms of the initial velocity and the acceleration. And this gives us this equation. So there's nothing new here, except, well, we can now use this equation, if we like, number 4, to find out how far did the car travel during the 15-second interval. So let's recall, what was the acceleration? 0.894 rounded meters per second squared was the acceleration, the constant acceleration that we found. So now, how far did the car travel during this 15-second time interval? So remember, the car started from rest. So if we like, we could just use this equation right now to find how far the car traveled. Since the initial velocity v0 is equal to 0, we can just eliminate that term here. 0 times anything is 0, so that term is 0. And remember, we decided, just arbitrarily, just make x0 equal to 0. Usually you can make that simplification. Another thing you could do is just move the x0 to the left side and just call the left side delta x after that. So then delta x would just be equal to these two terms. And since delta x is the displacement, and that's really what you're interested in, like the magnitude, the size of the displacement, is how far the car traveled. Anyhow, we just now have to put in, okay, during 15-second interval, accelerated at that rate, this gives us how far you go. So we could just put in our numbers now. And remember, we have to square the time. It's 15 seconds squared. So I came up with x equals 100.56 meters. Don't forget to handle your units. Second squared will cancel. Remember, this squared, that gets mapped onto both things here. So squared, this becomes 15 squared times second squared. So that second squared will cancel with this second squared. And you're just going to have 15 squared times 0.894 times 1/2. And my calculator determined that to be 100.56 meters. That's about a football field, a little more than a football field length that we went in 15 seconds, accelerating to 30 miles per hour. Is there another way we could have come up with the answer? Look over here. Car accelerates from rest to a cruising speed of 30 miles per hour in 15 seconds. So what would the average velocity be in that case? Remember, the initial velocity is 0. So the average, in this particular case, is going to be equal to the initial velocity, okay, is 0, plus the final velocity, okay, 30 miles per hour, divided by 2. So that's equal to 15 miles per hour. And here we're going to go 15 miles per hour for 15 seconds. I guess we could convert 15 miles per hour to meters per second. Maybe that's the thing to do. So I'm going to go, using this equation now over here, okay, x is equal to x0, remember x0 is 0, plus v average times t. Here v average is 15 miles per hour. Time is 15 seconds. Okay, so how can we go about this? Maybe I'll convert seconds to hours. Let's do it that way. Miles per hour times 15 seconds. But then I need 1 hour is 3,600 seconds. That'll convert that. That seconds will cancel with that seconds. This hour will cancel with this hour. And I'll get my answer in miles. So from down here, let me just call this star. Going up here. So moving star from down here to up here, the x that we just found. Doing this 15 times 15 divided by 1600. 15 times 15 divided by 3600 on my calculator, I got miles. The only units left standing was miles. Now, let me just convert that to meters. I remember that there was 1609 meters in a mile, and I get the same answer, as I must. So this x will also equal to that x. I just did the calculation again on my calculator, and I got the same answer, 100.56 meters. So both ways work. I can either use this equation or this equation. They're not the same equation, but they have the same information in them because this equation, number 4, derives from this equation, and this equation and this two mixed together. Okay, there's one more equation we want to get. Once we're done with that, this will be a wrap. There's one last kinematic equation we want to derive to complete our description. That'll be the 5th equation, and that will complete our description of kinematics, give us a complete set of equations that they derive in the book. Let's see, what did we do so far? Well, we derived these first 3 equations and said, well, that is the complete description. But then we eliminated the average velocity in this equation through this equation, and then we eliminated the final velocity through this equation into that equation that we had, and we got this. Now what we're going to do is we're going to again eliminate the average velocity, but then instead of eliminating for the final velocity, we'll eliminate for the time and see what we get. So we have 3 equations here. So for every equation, you can eliminate one variable. To get this equation, what did we do? We eliminated the average velocity. That was one variable we eliminated. And then we eliminated the final velocity variable. And we got this equation. For the next equation, we're going to again eliminate the average velocity. So we'll start the same way. So x is equal to x0. Then I'll substitute in for the average velocity with that. Okay, so that's going to be v0 plus v. So just sum the 2 over 2. So when the acceleration is constant, that's the average velocity. And only when the acceleration is constant, which is pretty much the only case we ever deal with. So that's going to be pretty much the case for us all the time. Okay, so that is the average velocity. And now the time. Okay, average velocity times time. Where am I going to get the time? I'm going to get the time from this equation. So I'm going to eliminate the time from this equation. So to get the time, what I'd do is I'd subtract v0 from both sides, and then that would leave me v minus v0 is equal to at. Then if I divide through both sides by a, then I would have time would be equal to v minus v0 over a. I'm saving some space for myself, just doing that in my head over here. If you need to, working with your pencil and paper that you got, taking your notes, go ahead and solve for that yourself. I'm just going to plug it in there so I can see what it is. If you do enough of this algebra, you'll be able to do it in your head, no problem. It's not that big of a deal. Okay, divided by a, and that eliminates for the time. Okay, so let's see what we get from that. I'm just going to have to go ahead now and do some algebra. There's no way around this. So let's see what I've got. So I got some stuff on top, and then on the bottom, all divided by 2a. So I got stuff on top here. So here we have v plus v0 times v minus v0. Essentially, I wrote it v0 plus v. Let me just rewrite that over here. So it's v plus v0 times v minus v0. If you work that out, when you have a case like this, the cross terms will cancel out. So v times v is going to be v squared. Then I'm going to have a minus v times v0 plus a v times v0. That minus and the plus are both going to add to nothing. They're going to knock each other out. And then we're going to be left with a minus v0 squared. So now what we can do is go, okay, well, what am I solving for here? I could solve for the final velocity in terms of the initial velocity. There's one more step to do over here. If I did that, I will get the final velocity, v squared, will be equal to the initial velocity squared plus 2a times the displacement, x minus x0. Okay, so what I did is just moved x0 to that side, then multiplied both sides by 2a, then moved the minus v0 over to the other side of the equation, and then rewrote the equation like this. And this is our last kinematic equation for 1D. We'll call it equation 5. I'm not sure how the book numbers them, but I'm numbering them 1, 2, 3, 4, 5. And this equation is useful if you're given the displacement and the initial velocity, and then either the final velocity or the acceleration, if those are the givens. We'll wrap up our discussion by using our new equation, equation 5, here in an example. So that is, suppose the problem statement is a little bit different. Suppose the problem statement is given that the car accelerates from a speed of 0 to 30 miles per hour in a displacement of 100 meters. So let's say instead of telling us the time it takes to make that displacement, they give us the displacement. They say a car accelerates from 0 to 30 in a displacement of 100 meters, or makes a displacement of 100 meters during that acceleration up to cruising speed. What's the acceleration? Well, then we could just use this. We can just use this equation that we just cooked up here, equation number 5, to find it in that case. Right, because we have the displacement, the delta x, that's equal to the delta x. 100 meters is x minus x0. And again, x0 is equal to 0, so we could just call that x if we wanted, or delta x. Doesn't matter. We're going to be looking for the acceleration. So the acceleration, just from this equation, is going to be just solving for it. And v0 is 0, take x0 to be 0. So just solving for the a, then in that case it's going to be equal to v squared over 2x, where x is just the displacement. X is just going to be the 100 meters. Okay, so v, what's that? Well, v is 30 miles per hour, but let's see, we have x in meters, so I guess we better get the 30 miles per hour in meters per second. So how could we do that? Maybe just look for another conversion factor online, just to maybe make it easier for ourselves. So I'm seeing online here, 1 mile per hour is 0.44704 meters per second. Maybe we'll just use 3 sigs. 0.447. So 1 mile per hour is 0.447 meters per second. So I think we could just use that quickly to convert 30 miles per hour to meters per second. So here's our final velocity. 30 miles per hour times the conversion factor. You'll get miles per hour canceling with miles per hour. I got 13.41 meters per second. So now we just want to put all that information in over here. 13.41 meters per second, all squared, divided by 2 times the displacement. Here we're just rounding to 100 meters. And I'm getting right over here, a acceleration is equal to 0.899 meters per second squared. Up to rounding error, that's roughly, or that is the same as the answer we got above. So now we derived all of our 5 here, but they all really come from these 1, 2, 3 kinematic equations in 1D, and we've showed examples of how to use them. Okay, that's it. We'll catch you on the next lecture video.